Hello. In this content, I am going to start a very interesting topic of mathematics. But before we start, let's discuss something. Here you can see the numbers like 1, 2, 3, 4, 5 and so on. What's that? Yes, that is the set of natural numbers. Then it's 2, 4, 6, 8. What's that? Exactly. That is the set of even numbers. And suppose if we just take like that 1, 3, 5, 7, that will be the set of odd numbers. But suppose if I am taking that 1, 4, 9, 16, 25 and so on, what's that? Yes, that is the set of square of natural numbers. What these polar numbers look like? Yes, they are the series. Can you tell me the sum of 1 to 100? Yes, you can. Of course you can. But the condition is you have to tell me without calculator. Again you can, but you need more time. Let's see that how to do it without calculator and differently with the great mathematician Carl Friedrich Gauss.
In 1787, young Carl was a 10-year-old student in Braunschweig, Germany. The pattern that was perhaps most apparent in his class was the tedious repetition of a dismal life, toiling over slates in a drab, low-ceiling classroom and avoiding beatings from the abusive teachers. There was an instructor at the school by the name of Büttner. Although he enjoyed intimidating his students, Büttner often found that teaching involved too much work. He therefore devised ways to keep his students busy for hours on end while he sat back to relax. On one occasion, as the story goes, he gave his class the task of adding together all the numbers from 1 through 100. This, he had hoped, would earn him a relaxing afternoon of watching students tap away at their slates. He had barely finished his instructions when his student, the young Carl Friedrich Gauss, stood up from his desk, walked up to the front of the room, and turned in his slate on Büttner's large desk with an offhanded, "There you go." Young Carl sat quietly for the rest of the afternoon as his fellow students finished their addition, and Büttner planned how he would beat his arrogant student for avoiding his classwork. One by one, the other students finished and placed their slates on top of Carl's. When all of the slates were turned in, Büttner immediately ripped Carl's slate out from the bottom and looked at it. To his astonishment, he found that Carl had the correct answer, and the only number on his slate was the answer. He had written no calculations whatsoever. How did he do it? How had he figured out how to avoid such boring, repetitive work and still produce the correct answer? Let's see if we can start to find a pattern to Büttner's horrible addition task. If you start writing out the numbers 1 through 100, or even start punching them in on a calculator, you should notice a repeating pattern. If you look at the problem in chunks, you are adding together the single digits 0 through 9 a total of 10 times, and adding together 10 tens, 10 20s, 10 30s, and so on. The addition problem may seem daunting when you first look at it, but once you start solving it, you can see that it's just screaming out with possible patterns. It's not completely clear what approach Gauss actually used, but more than likely, with the speed at which he solved it, he probably thought along these lines. Let's think of all the digits as being drawn out in a long row end to end. On the far left is 1, and the far right is 100. If we add the first and last number in the sequence, 1 and 100, we get 101. If you look one step in from these numbers to 2 and 99 and add them together, you also get 101. Move in another notch to 3 and 98, and they also total 101. This pattern continues throughout the sequence of numbers until we meet at the center with 50, plus 51 equals 101. We've seen that arithmetic statements can also be encoded with shapes. To make the pattern perhaps a bit more obvious, let's picture the numbers 1 through 100 as little squares. The number 1 is represented as 1 square, the number 2 as a stack of 2 squares, the number 3 as 3 squares, and so on. All the numbers stacked up one next to the other form a sort of triangular staircase. The task now becomes to count the total number of squares. Previously, we used multiplication to determine a number of tiles arranged in a rectangular shape. But now we don't have a rectangle, but a triangle, which we don't yet know how to deal with. Perhaps we could find a way to turn this triangular shape into a rectangle. We could divide the triangle into 2 parts right between 50 and 51. We could then take those 2 chunks and fit them together like puzzle pieces to form a rectangle. The single square is moved on top of the stack of 100 squares. The 2 squares are on top of the 99 squares, and so on, all the way down to the 50 squares on top of the 51 squares. Moving around this piece hasn't changed the total number of squares. We simply worked to rearrange it into a form we could more easily deal with. The figure is now a rectangle that has 50 squares across and 101 squares running up the height. Multiplying 50 by 101 gives us the total number of squares, 5,050. When we look at the problem in this way, we see that it isn't a hassle to add together any series of numbers. Let's look at the diagram and see if we can find a general description for the pattern. The height of the rectangle is the sum of the first and last number. The width of the rectangle is the total number of digits being added, divided in half. These 2 quantities define the edges of our rectangle. To find the area of the rectangle, we simply multiply the height by the width. Suppose Büttner had wanted a full day of rest and asked the students to add together all the numbers from 1 to 5,000. Even though the numbers are now much larger, the same pattern applies. The first number in the series, 1, plus the last number in the series, 5,000, total 5,001. The total number of digits being added is 5,000, and half of that is 2,500. In this series of numbers, we could add up the sum 5,001 a total of 2,500 times. The answer is 5,001 times 2,500, which turns out to be 12,502,500. Why stop there? So far, all of the series we've worked with have started with 1, but they don't have to. Let's add up the numbers between 5,001 and 7,000. Just because the numbers are now bigger doesn't make the pattern itself any more complicated. We can encode the numbers again as little squares making a staircase, but this time the low end of the stairs doesn't reach the ground but starts up at 5,001. We aren't figuring out how many squares make up a triangular staircase, but we can still apply our pattern of cutting the shape halfway across and stacking the pieces to make a rectangle. 5,001 added to 7,000 equals 12,001. There are a total of 2,000 digits being added, and half of that would be 1,000. We're adding the sum 12,001 a total of 1,000 times. We multiply 12,001 by 1,000 to get 12,001,000. we were able to add up 2,000 numbers for a total over 12 million in just a matter of seconds. There you go. Carl Friedrich Gauss went on to become one of the most influential mathematicians in history and was among the first people to make a fundamental change to some ideas that had lasted for centuries. He was without question a brilliant man, but don't regard him as some sort of inaccessible genius with a giant pulsing brain beyond the comprehension of mere mortals. When you look at Gauss's method of breaking down the task of adding together a sequence of numbers, you can see that it uses only basic arithmetic and is relatively simple. If the only thing we take away from this is a way to quickly perform addition, we'd be missing the big picture. The important aspect isn't the answer, but how we found it. Beyond adding together numbers, his method can give us an example of how to harness logic to break down a seemingly hard task into an easy one. In general, what it takes to solve complex problems often isn't sheer brain power, but a novel perspective to see the situation in a new and often simpler way.